Hi students. So today we will discuss the principles of computer design. So as we have already discussed in the previous classes, how the performance of the two different computers can be evaluated. From the previous discussion, it was concluded that the normalized estimated time along with the geometric mean is the best way to perform or to compare the performance of the two computers. So whenever we want to find the relative performance of the two or more than two computers with respect to a reference computer, normalized execution time along with the geometric mean can be used. The similar approach is also used in the spec benchmark. After the evaluation of the performance of newly designed computer with respect to the already reference computer, if we find that whatsoever the performance we have evaluated is not as per the expectation of the design, whatsoever expectations of the design was, we are not able to get that particular performance from that particular machine. So naturally, once we will not get the results as per our expectations, then we will have to improve that particular design during the design analysis. So this particular lecture will be focused on how can we improve or enhance the performance of a designed machine. What will be the different approach will we use to perform the improvement, and how much enhancement in terms of quantity will we get after the improvement of a portion or a whole machine. So this is the focus of this particular lecture. So first of all, we will try to understand what is the need of the computer design and its analysis. As we have already discussed that after the evaluation of parameters, whatsoever the parameter will we evaluate and whatsoever the method we will use to evaluate those parameters, we will be able to get the performance of our newly designed computer. If we will use the spec benchmark or any other methodology in which we are going to perform the relative comparison, then we will get our performance in terms of whatsoever already existing is. Whatsoever the performance we are getting through the evaluation methods, and if we want to improve the performance of machine during the redesigning and analysis of that particular machine, what will be our approach to improve the performance during the enhancement of that particular machine? We will consider the two different cases. We will differentiate the whatsoever the tasks are performed by the computer on the basis of common cases, which will be the frequent cases, and infrequent cases, which will not be the common cases. Where the meaning of the common cases will be, it will be a set of programs, it will be a portion of the hardware which we or a computer will use many times, frequently will use to perform its operation. And on the other hand, whatsoever will be infrequent case, that will be a set of instructions, set of hardware which the computer is not going to use frequently. Computer may use that particular portion once a while. So on the basis of these two cases, one common cases, another is which is also known as the frequent case, and another infrequent cases. Usually we will try to improve or enhance the performance of frequent cases rather than rare cases. For the better understanding, we will try to compare it with an example. Let's suppose we want to design, or we have designed a ALU, arithmetic and logical unit, which is used to add two numbers. So what will be the role of the ALU? The role of the ALU will be to perform the arithmetic operation, logical operation. Let's suppose in this particular case we want to perform the addition of two numbers. So what will be the role of the ALU? ALU will get the two operands either from the within the processor or from the memory. It will get that particular operands and then will add. After the addition, the result which will be there in ALU register, some flags will also be affected. And the role of these flags, which will be there in a program status word, will use to gives us the status of the result. Most commonly flags which we are using are carry flag, parity flag, overflow flag, sign flag, auxiliary carry flag, and many more. Let's suppose we are considering carry flag, parity flag, and all other flags are the frequent cases, and overflow flag is infrequent case. So now what is the meaning of this? Overflow flag will be a flag which will be used to indicate or which will be set in that particular case whenever the sign of the number will change after the execution of the number. For example, let's suppose we are going to add two signed number and both numbers are say positive, and after the execution, if the MSB will become 1 due to the values of these two numbers, then overflow flag will have to be set, and which will indicate that your sign have been changed. We were expecting the positive result, but we are getting the negative number. So now why we are calling overflow flag set is a rare case. The reason behind it, the reason is if we are going to perform the arithmetic addition operation with the unsigned number, in case of unsigned number, we are not going to bother about the sign of the number. Then even if overflow flag will set, we are not going to bother about that. So, but in a special case, whenever we want to perform the addition with a signed number, then again, in case of signed number, every time overflow flag will not set. Overflow flag will set in only in those cases in which sign bit will change, which will be the MSB. Sign bit will change from 0 to 1 or 1 to 0 for positive or negative number in that particular case, and this will be considered as a rare case. So that is why normally we will consider the no overflow flag is frequent case, because normally there will be no flag set from the outcome of the two numbers. Particularly in the case of unsigned number, there will be no overflow flag, and moreover we are not going to bother about the overflow. So the rare case will be overflow flag will set in case of signed number. So now the question is, which portion of the ALU we will try to enhance or we will try to improve the performance? So what will we do? We will go with the optimized case, and that will be the common case. And what is the common or frequent cases? Are with no overflow flag. So which means we will not improve the performance of overflow flag because it is a rare case. So we will improve the performance of the circuitry or instructions which are not going to affect the overflow flag. So now what will happen if we will go with this particular approach? If we will go with this particular approach, naturally we will improve our we will improve the performance of our arithmetic and logical unit. And what will happen if the rare case will occur? No doubt, if a rare case will occur, the performance of the ALU will slow down because we have not done anything. We have not improved anything in the machine for the overflow case. So naturally, in case of rare case occurrence, the performance of the ALU will remain same as it was in the case of before enhancement. But this will be a rare case. We are not going to improve the rare case at the first instant. At the second instant, we can also include the rare cases as well. So this is the approach. This is the methodology which we will actually use while improving the performance of the computer design to enhance the overall performance of the already designed computing machine. And to do so, Amdahl's law is used to quantify the what amount of improvement, what amount of enhancement we want to get in terms of speed, in terms of fraction, what amount of portion we will have to enhance, and what amount of enhancement will we do. All these things will be included in the Amdahl's law. So next slide we will discuss what is the Amdahl's law. As per the Amdahl's laws, we have already discussed that whenever we want to enhance or improve the performance of a computing machine, Amdahl's law is used to quantify the performance of a machine with enhancement feature after the incorporating the enhancement feature as compared to the whatsoever the original machine we are going to compare. So Amdahl's law will tell us how much improvement in terms of quantity will we get in terms of performance of enhanced machine with respect to the original machine. So Amdahl's law also states that the performance of improvement to be gained from using some faster mode of execution is limited by the fraction of time the faster mode can be used. Okay, so the enhancement to the machine that will improve the performance when it is used is called speed up. So the first term, the first parameter which we will use to evaluate the improvement of the performance after the enhancement in the machine will be the speed up. And speed up can be defined as what? Performance. If we are going to evaluate the speed up in terms of performance of the enhancement machine with respect to the without enhancement, then it can be written as performance by using the enhancement feature for entire machine entire time upon performance without using the enhancement feature. Okay, so it will be the ratio of the performance with the enhancement feature and without enhancement feature. As we know that the performance of a computer is inversely proportional to the execution time of a computer. So naturally, if we will want to evaluate the speed up in terms of the execution time, then it will be opposite to this. So it will be the ratio of the execution time without using the enhancement feature to the execution time when we are using the enhancement feature for the entire time. So this is the one parameter speed up which is used to evaluate the improvement in the performance after incorporate enhancement features within the machine. So next is the fraction enhanced. This is another term which we will use actually. What is the fraction enhanced? The fraction enhanced will be a term which will be defined as a fraction of the total computation time of the original machine which can be enhanced to improve the performance. For example, say we are having a machine and we want to enhance the performance of that particular machine. One thing is we will enhance the performance of each and every part, hardware and software part of the machine to get the enhancement. That is a very difficult task. So what the designer will do, the designer will try to improve a fraction of the total computation time of that particular machine. So what is the amount of a fraction we are going to enhance out of whatsoever the total computational time of the original machine is, that is called the fraction enhanced. So it will always be less than 1. Okay, so now what is the speed up? It is another parameter which is called speed up enhanced. This speed up enhanced will be, it is called as improvement due to the enhanced execution mode. So it will be defined as term which will be the improvement due to the enhanced execution mode. Whatsoever enhancement we have done in the execution mode, and due to that enhancement, what is the improvement in the performance in terms of speed, that is called speed up enhancement. Speed up enhanced. So it is how much faster the task will run if the enhancement mode, the enhancement will be used for the entire program. It will also give us this idea. Okay, so what is the enhanced fraction or fraction enhanced? It is the fraction of the total computation time out of which we are going to enhance. It will also a portion of the machine which we are going to improve or which we are going to enhance to improve the performance of the machine. Now we will also be interested to calculate the execution time of new computer. what will be the execution time of the new computer, and that can be calculated as it is the execution time new will be equal to the execution time old into 1 minus fraction enhanced, 1 minus fraction enhanced into fraction enhanced upon speed up enhanced. So this is the way how can we calculate or how can we evaluate the execution time for new machine after incorporating the enhancement. What amount of fraction we are going to enhance, this new time will depend upon that factor as well. Okay, so once we will enhance a portion of the machine, we know what is the speed up of that enhanced portion, what is the new execution time. So after knowing the execution time of enhanced machine with reference to the fraction which we have already enhanced, we will be interested to know the impact of on the overall speed of the machine due to whatsoever the enhancement we have done in the old machine. That particular parameter can be evaluated by using this equation, and it will be execution time old upon execution time new. So if we will replace this execution time new with this particular equation, then we will get what it is, 1 upon 1 minus fraction enhanced plus fraction enhanced upon speed up enhanced. So this is the way how can we quantify the amount of improvement after the enhancement in the redesigned machine with respect to the without enhancement machine. So this is all about the Amdahl's law. Now we will try to understand the physical significance of the Amdahl's law with respect to the different examples. We are considering an enhancement that runs 10 times faster than the original machines. Let's suppose we have made some enhancement in the machine, and that enhancement, whatsoever the enhancement or improvement we have made in the machine, that was the 40% of the total time, whatsoever the total execution time of that particular machine, out of which we have made the changes only for a 40% portion of the total time, and whatsoever the improvements we have made in the 40% of the total time, that particular improvement gives us the 10 times faster. The speed of the resultant machine was 10 times faster than its original machine, but it was only for 40% of the time. So we will try to calculate what will be the overall speed up gained by the machine after incorporating the enhancement of the machine. So as we can see, it is given fraction enhanced will be equal to 0.4 because we have done the enhancement on the 40% portion of the total machine, either on the software model or on the hardware model. This is not given in this particular example, but we have done the improvement. We have enhanced the performance of the machine on the 40% of the portion of the total machine. So the fraction of the enhanced will be 0.4, and once we will enhance the performance on the 40% of the portion of the total machine, it gives us the speed of that particular portion was 10 times faster than the whatsoever the speed was before the whatsoever the speed was of its original machine. So speed of enhance will be 10. So if we will have to calculate the speed up overall, if we will try to calculate the impact on the overall impact on the speed, so now we will try to calculate the impact of this enhancement on the performance of total machine or overall performance on the machine, that we can calculate by using this equation as we have already discussed this. So by putting the value of fraction enhanced and speed up enhanced, we will get this equation, and after solving it we will get the final speed up overall will be 1.56. So it means the impact of this enhancement which we have done at 40% of the total machine was able to improve the performance of total machine 56%. Okay, so this is the impact of enhancement on the performance of the overall machine. Okay, so now again we will try to calculate or try to understand the concept with the another example by using the Amdahl's law and whatsoever we discuss in this lecture. In this particular machine, what is given? Given is, let's suppose we want to implement a floating point square root for its graphic processor. Let's suppose we will have to write a program along with its hardware. Let's suppose we want to develop a floating point square root hardware along with its software for the graphic processor of the main machine. Suppose that whatsoever the floating point square root we have designed, it is responsible for the 20% of the execution time for a critical benchmark. So whatsoever the floating point square root we want to design or we want to implement is contributing to the 20% of the execution time for the whole machine. The designer decide to go with the two proposals, or designer proposed the two solutions. One proposal was to add the floating point square root hardware, which will speed up this operation by a factor of 10. If designer has planned to, or designer has proposed to include a hardware for the floating point square root which will increase the speed of operation by a factor of 10. This was the one proposal. And second proposal, what? We will not introduce any hardware, we will just improve the floating point instructions, which will make that particular program fast. And what will be the change in the instruction? What will be the proposed enhancement? That enhancement of floating point instruction will be responsible for a total of 50% of the execution. Whatsoever the instruction they want to improve, that particular instructions are contributing the 50% of the total execution time. So the design team believe that they can make all FP instructions, whatsoever the instructions, floating point instructions was there in the instruction set, if they will improve the floating point instructions, then there will be improvement, 2 times improvement in that overall machine. Okay, so now we will have to compare the performance of two design alternatives. Whatsoever the alternative they have proposed to improve the performance, we will try to understand which approach will be more beneficial for the designer. So first of all, we'll consider the first case, in which improvement in the hardware. So what is given? Given is whatsoever the hardware will be improved, that particular hardware is going to contribute 20% of the total machine. So the fraction of enhanced will be 0.2, and whatsoever after the improvement in the hardware, the speed of the resultant portion will be increased 10 times. So that is why speed up enhanced is 10. So this is the equation which we will use to calculate it. And speed up for floating point square root hardware with the given parameter will gives us what? After the putting of value, it will gives us 1.22, which means if we will improve the hardware of the machine under the given circumstances, it will gives us the improvement, or will speed up will be 1.22. Okay, so now we will consider the second case. If we will go to improve the software, in which all the floating point instructions will have to be improved, and as it is given in the statement, all the floating point instructions are having the 50% weightage of the total time. So the fraction enhancement will become 0.5, speed up enhanced will become 2. So again we will calculate the speed up for the floating point instruction. After putting the given values, we will be able to get 1.33. So 1.33. So what does it mean? The meaning of this is which approach approach will gives us the better result? Second one. So why the second case is better than the first case? Because the frequency of occurrence of floating point instructions is high. It is 50%. So that is why we are getting better performance in case if we will enhance the floating point instructions. So with the help of these two examples, we will be able to understand in a better way what is the role of the Amdahl's law and how we are able to evaluate or calculate the improvement after the enhancement in terms of quantity. How we'll be able to predict the quantity of improvement after the enhancement. Thank you. Thank you.